let's continue talking about kinetics, the study of the speed of a reaction. We are working in section 19.3 where you are learning how to calculate the rate of a reaction. And where we left off, I said the rate of a reaction was measured in terms of the change in concentration of anything in the reaction, a reactant or a product, it didn't matter. The change in concentration of something over a particular change in time. So the change in concentration, and we're going to see that in some reactions we're actually going to measure this in terms of the change in pressure rather than the change in concentration, so that will come up. The change in concentration can be in terms of any reactant or product, and it literally is anything. When you are measuring the rate of a reaction, you're going to choose the reactant or product that's easiest to measure. That's how you'll make this decision. So, for example, if we were looking at the reaction N2 gas plus 3H2 gas, which makes 2NH3 gas, and we wanted to measure the rate of this particular reaction, the rate can be calculated or measured three different ways in terms of the production of the NH3. So this would be the increase in the amount or concentration of NH3, or since it's a gas, it could also be measured in terms of its pressure, the increase in the pressure of NH3. Or we could measure it in terms of the loss or the consumption of N2, the reactant, or H2, also a reactant. So we could pick any one of these three things and monitor either how quickly it's being made or how quickly it is being consumed and calculate the rate from that. We're going to start with a really generic. Consider a generic reaction. So this is going to be a reaction where we have one reactant, which we're just going to call A, and it's turning into one product, which we're going to call B. This is not necessarily one-to-one stoichiometry, but it is one molecule turning into one molecule. So some examples, if you're having a hard time visualizing what that might look like, 3 O2 gases turning into 2 ozone. That would be one example where O2 is A and O3 is B. Or another example, Cl2 gas turning into 2 Cls. So that again, one reactant, one product. Stoichiometric coefficients could be anything. But this is a really simple and easy reaction for us to start with to study. This A goes to B reaction. So if we wanted to measure the rate of an A goes to B reaction, we could either monitor the production of B, or we could monitor the loss or the consumption of A. And we would get some equations that would look like this. So if we were doing this in terms of B, and we were monitoring the production of B, we could say that the rate of this reaction is the change. Remember, that triangle is Greek letter delta, which is our scientific symbol for change. The change in the concentration of B using the square brackets like we used in equilibrium. Remember, when we put something in square brackets, it just means, that's another way of saying the molarity of that substance. So we're looking at the rate in the change of the molarity of B over the change in time, which we'll abbreviate with a lowercase t. Or if we would rather focus, for our generic reaction, if we'd rather focus on A, we could say that the rate of this reaction is the change in concentration of A over change in time. Now, if we just plugged these numbers, delta A over delta T versus delta B over delta T, if we just plugged them in like standard final minus initial, we would end up mathematically with the same numerical value of rate, but they would have a different sign because one of them is being made and one of them is being used. So in order for us to get the exact same number, not just the same value, but also the same sign, we're going to put this negative symbol in front of A, the reactant, because it's actually being used up. So the negative sign, this is going to be in front of all of our reactants. And this is just so that the value of rate is always the same. Whether the substance is being produced or whether the substance is being used up. And if that feels a little bit confusing to you, we're going to draw a picture here that might make more sense. So let's make a graph of this A goes to B reaction. And we're going to have molarity on the y-axis, and we're going to have time down here, and we're going to graph A goes to B. So we start this reaction with A, with some amount of A, because it's our reactant. Let's say we're starting with this much, whatever that might be. Let's say maybe it's 5 molar. And over the course of time, the amount of A drops. Something like this. It drops exponentially at first because initially there's a lot of A molecules and it's really easy for them to react and find each other and do whatever they need to do. But as time proceeds, the rate of the reaction slows down, so the change isn't as exponential, and eventually it just flattens off. And notice that I've made my A not go all the way to 0. This just means that the reaction never uses up all of the A. So this would be maybe like an equilibrium thing. This reaction doesn't completely use up all of the reactant. And again, the reason that I know that is because I'm ending with this much of my A molecule. I'm not dropping it all the way down to 0. And I just chose to do it that way just for fun. So let's draw B on here. Oh, let me label this. This is our A. So now let's draw B. B as a product, let's say we're starting with 0, which is pretty reasonable for a product. We don't have any in there to begin with. And our concentration of B is going to increase exponentially, just like A decreased exponentially, and then it's going to level off at about the same time as A levels off. So here is our B. So this is a graph that's just showing the concentrations of these things over time as the reaction proceeds. And the rate, if we wanted to measure it in terms of B, we would say that it is like the final amount of B, which is right here, minus the initial amount of B. So that's going to be change in concentration of B, and that'll be a positive number, divided by, so this, let's put in here, this is our delta B. And that will be divided by the final time minus the initial time. So this would be our delta T, like that. And whatever that number might be, we'll calculate some of these on ALEKS. If we wanted to do this in terms of A, so let me just kind of get these red ones out of the way. If we wanted to do this in terms of A, this would be our final, which is right around here, minus initial. This is our delta A. And final, for A, the final is a smaller number. So our change in A is going to end up being a negative number because we're taking a small number minus a big number, which is why we've got to put that negative sign in front. It's really just kind of like an absolute value thing, divided by the change in time, which wherever we choose to stop this, there's our delta T. That's going to be a positive number because it's big final temperature or final time minus small time. So let's write down for all of these that the rate, no matter what we're calculating, the rate is the final concentration. Like for B, it's B final minus B initial over T final minus T initial. If we're doing this for a reactant, our rate is going to be negative A final minus A initial over change in time. Oh, no, I'm trying to write it out. T final minus T initial. Okay, let's go practice this on Alex.